All right, next up are acetals. So very similar to the hydrates, except instead of using water, we use an alcohol instead. Note these are always formed under acidic conditions. Later on in the course, we'll take a look at what happens here under basic conditions. Some cooler stuff, but we'll save that for later. Anyway, so we're going to switch from our carbonyl over to our acetal, which is basically two ethers. You can kind of think about it. This H plus here acts as a catalyst. And so remember, that means that it's regenerated in the reaction. Overall, let's go ahead and draw the mechanism of this reaction. So first off, we have our carbonyl, and it's going to pick up the proton because we are under acidic conditions. After that, we're going to have our alcohol attack, as we've previously seen with water, nothing really new here. Right, then our alcohol is positively charged. We're going to have some proton transferring occurring here. With the end result, we're going to form some water and then our OR. And then at this point, our OR is going to kick its lone pair back down and then kick off this water molecule. Go and draw this down here. And so at this point, we've kind of reformed at least a carbonyl type of thing. And then we have another alcohol come in and attack. And then, of course, a proton transfer to get rid of any positive charge. And then we have our acetal. Note that it's important that this be shown in 2 steps, right? So we have to kick this lone pair down here and then kick off the water. Oops, I forgot the positive charge on the water. You're not allowed to basically draw your alcohol coming in here and then doing that, right? So I know it seems kind of like a shortcut, but there's a lot of evidence that says that doesn't occur. So we want to kind of keep it correct. Similar to our hydrates, acetals are generally not favored in terms of our equilibrium. But what's cool about acetals is we can make them favorable. And so let's take a look at the overall reaction. So what we have here is our carbonyl. And then we have some kind of acid catalyst that'll produce our acetal, and then a molecule of water. And so in general, right, the reactant side is favored. But what we can do is we can take this water that it produced and we can distill this off. And then when we distill off this water, we're going to decrease the concentration of the water. And according to Le Chatelier's principle, we'll shift our equilibrium towards the right because we're removing our product, right? So think back to Gen Chem, that's Le Chatelier's principle. If you remove some of the product, you'll shift the equilibrium towards the product, right? Or towards whatever side you're removing the stuff from. So that's the cool thing with acetals. Even though they're not favored, we can make them favored by doing this. Another cool thing with acetals is that we can make them, that they're good leaving group. So for example, this diol is often used to form this relatively stable acetal. And so this acetal can serve as a good protecting group. Right, similar to the trimethylsilane that we saw earlier, but let's take a look at how this acts in action. So for example, if we have a ketone and then an ester, right? So this over here is our ketone, while this over here is our ester. If we react this with our protecting group, and of course the catalytic amount of acid, it will selectively attach to our carbonyl or to our ketone or aldehyde, right? It won't go after the ester. And so now what we've done is we've essentially blocked or protected that ketone group, and now we're free to do chemistry on the ester in this case. So there's all kinds of stuff you could do. Maybe you want to do a Grignard over here, or maybe you just want to straight up just reduce it. We could reduce it, using lithium aluminum hydride. For example, get it down to an alcohol. And then if we want to deprotect our group, we just have to add some acid, generally aqueous acid, so generally H3O+, right? We're adding that water that we removed to shift the equilibrium to the right. Now we just add it back in, and then we shift the equilibrium back to the left and regain our carbonyl. Right, so something like that. And this acetal group is generally unreactive towards like nucleophiles, right? So you can have all kinds of nucleophiles or even bases attack. It's relatively unreactive to bases. It's only reactive towards acids, right? So in that case, that H3O+, which is how we get rid of it. There's also something called hemiacetals. And in this case, hemiacetal is between an acetal and a hydrate. So in this case, we have one OH group and then one OR group. They're generally unfavored, but there are some cases where they are actually favored. The most kind of common one is glucose, which is, the sugar in your blood and whatnot. So if you think about that, it actually does have a cyclohexane structure. So bringing back some 112 there. Right, so we have a hemiacetal right here. This carbon right here that I colored green is a hemiacetal. On one end, it's got an ether, and then on the other end, it's got an alcohol. Of course, glucose is free to exist as this 6-membered ring, or it can open itself back up to get this version of it instead. Let's see, wedge OH dash OH dash OH dash OH, and then the aldehyde at the end, right? So these two ends can react with one another to form or to join together or not join. We'll touch on that a little bit in the biochem section, but of course, if you take a biochem course, you'll go much more in depth. But organic chemistry does generally form the basis of biochemistry.